Hello everyone, welcome to this video. In this video, we are going to learn about the adaptive spiking neural network using OpenMathAI. So, let's get started. What is an adaptive spiking neural network? An adaptive spiking neural network is a deep learning model designed for temporal data processing, pattern recognition, and prediction. Unlike traditional neural networks, which process continuous numerical values, an adaptive SNN processes information through spike-based neuron activity while allowing neurons to adapt their firing behavior over time. An adaptive SNN consists of an input layer, adaptive spiking neurons, and an output layer. The input values are converted into spike signals and passed through adaptive neurons that automatically adjust their firing thresholds based on recent activity. This adaptive mechanism enables a network to efficiently capture temporal patterns while reducing unnecessary spikes. During prediction, the input signals activate the adaptive neurons, which process both current and previous information. The learned spike patterns are then passed to the output layer to calculate the final prediction. We will use an ECG arrhythmia risk prediction dataset for the adaptive SNN model. This dataset contains 1,500 data samples. The input features are ECG voltage and motion acceleration, and the target output is arrhythmia risk. The arrhythmia risk depends on the relationship between the ECG signal and body movement. During training, the adaptive SNN learns these temporal patterns by adjusting its neuron thresholds and optimizing the network to predict the arrhythmia risk accurately. Once the model is trained, OpenMathAI uses a learned adaptive spiking behavior and network parameters to predict the arrhythmia risk for new ECG measurements without retraining the model. So, let's get started. Open OpenMathAI. Click Create New Project. Enter the project name as Adaptive SNN. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Enable the dynamic case, states, because adaptive SNN is a dynamic model. Configure the dataset by specifying the inputs, feedback states, and targets. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Feedback allows a previous reservoir state to influence the current state, enabling the adaptive SNN to remember recent information. This short-term memory helps the model capture temporal dependencies and improve prediction for sequential data. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature is signal diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the Adaptive SNN model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also the another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of parity, residuals, and residuals histogram and predicted output. Click Math and Code Preview to view the mathematical model generated by OpenMathAI. The complete adaptive spiking neural network architecture, generated source code, and training details. Open the Math view to visualize the complete Adaptive SNN model. Maximize a window and scroll down to see the input layer, recurrent reservoir with 400 spiking units, readout layer, output prediction, the feedback recurrence path, and the complete network structure. The visualization shows how input features are converted into spike signals, processed through the recurrent reservoir, and passed to the readout layer for prediction. The input layer sends the scaled input features to the recurrent reservoir, where 400 adaptive spiking neurons process the spikes, automatically adjust their firing behavior based on recent activity, and learn temporal patterns through recurrent connections. The readout layer combines the reservoir states with the current inputs to generate the final prediction. The skip path directly connects the input to the readout layer, while the feedback path preserves short-term memory by allowing previous reservoir states to influence the current state. After training, OpenMathAI uses a learned adaptive reservoir dynamics and readout parameters to predict outputs for new input data without retraining the model. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSI C, MCU Fixed Point C, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.